We're on the last part of the chapter. We're going to talk about reaction mechanisms. And reactions, if you think about like anything you do in life, it happens in steps. Maybe it's just one step, maybe it's 2 steps, right? 3 steps. But like if you made a list of like how you went grocery shopping or how you put your shoes on or all that, there's always going to be steps. And so what a reaction mechanism does is it tells us how these steps occur in order for you to get your products. So like, right, you get ready for in the morning, and let's just generalize. You have shoes and you have pants on, I'm assuming. I don't know. Right, what do you put on first? Come on, guys, it's not that hard. Get up in the morning, take a shower, get past all hair stuff. You got shoes and you got pants. What do you put on first? Pants, right? Why? You can't get your pants on if you have your shoes on. It's hard anyways. Look at the size of my feet. It just doesn't work. Although, yeah, I got baggy pants on today, so it might work, but still, that's different. Right? All right, so this is what we're going to do. We're going to look at how a reaction takes place. So hopefully this will work today. I wanted to run some of these yesterday on Monday, but it just wouldn't go. So this is how this reaction takes place, and we'll talk about the reaction itself in a second. It's a video, and she's talking. All right. So let's write out what we saw, okay? So, oh yeah, I can write on this one. I had chloroform, which is CH3Cl, and there was a fluoride ion, okay, and then it made CH3F, that's what you see up on the screen right now, right, plus Cl minus. Now, did you see how smooth the transition was? As the one came in, pushed the other one out, and it happened all in one step. Okay. Your pants don't even go on in one step for most people. Most people stick one foot in and then the other foot in, and that's actually multiple step process, right? And unless you sit on your bed and then you pull your pants over both feet. Does anybody actually put both legs of their pants on at the same time? Weirdo. Do you lay on your bed in the morning? Yeah, that's what my daughter does too. She like gets on. She's like, "Get up!" And then when she's really feeling lazy, she just leaves them on. She puts them on at night. She wakes up in the morning. She has her pants on. I'm like, "What are you doing? I just can't be comfortable." But,
genius.
yeah, it's genius. She's saving those extra times, avoiding Starbucks, all that kind of stuff. Yeah, today was foggy day schedule, so that makes it even worse in some ways because you get to sleep in on a foggy day schedule, and then you have to get. Sorry. Okay, so yeah, that's a one-step mechanism. So we're going to call that. We're going to label this one step. It's an N. All right. So let me show you the other one. Okay. And I'll write this back up here, but you tell me how many steps you think you see here. I'm going to write this one up on the board, and I'll try to get it up on the screen too, but it's a little more complicated to watch the video and write at the same time. And count the steps in your head. How many steps?
5.
Some people see 5. 3? It's 3. So what are the 3, right? So let's go back to the beginning. So I have the first step is that gets attached, right? So you saw the charge move over, maybe? Yeah. So that actually all happens in one smooth step. And then this breaks, so that's 2. Again, if you counted the charge moving, you get 5. Right? And then the last one is the Cl moves in while the OH moves out, or the H2O moves out. So this is a 3-step mechanism. This is actually these two mechanisms are well established. This is how these reactions take place. And the reason this is important is depending on which step is the slow step, that's what we see in the kinetics of the reaction. See, not all these steps happen at the same speed. But the slowest step determines what we see in the rate law for the reaction. Okay, so let me write that out here. Okay. Let me just put some notes here. I'm gonna write this mechanism over here in a little bit. But there were 3 steps in this mechanism. Okay, and then I'll write them out in a little bit. But not all the steps happen at the same rate. And the reaction rate law represents the slowest step in the reaction. What we see as the reaction rate law is represented by the slowest step in the reaction. Let me say it that way. I'll say representative since I already started writing. Okay, so let me write these steps out. I'm going to write them on the board, except for these people, these animals just walk up with the markers every time. If I do it in Sharpie, that would piss them off. Wait, there it is. So in my first step, I had CH3OH. Sorry, that's not what I had. I had this C, and then there was CH3OH, like this. Oh, you know what I'm going to do? Let me make a gap in here. I'm going to put this, there's a single bond in here, so I'm going to draw it like this, okay? And the oxygen had lone pairs on it. And then I had H+. And the first thing that happens is the H+ attaches to the electrons, right? So in this first step, I ended up with this. And then they showed this. That's the first step from the video, right? Going back here. That was that. The H comes on and attaches itself. What's the next part?
The charge moves.
Was that?
The charge moves.
The charge moves. And again, that actually happens at the same time that the attachment gets made, but it's a little hard to. And then after that, what happens? Breaks off. Yeah. So I have C. So I'm going to start with this. This is how you do the next step. You start with what you ended up with over here, and you rewrite it over here. And I'm going to draw this out just to emphasize. It's the same structure. Again, I should probably be complete here. I can put those guys in there. The next part is the OH, H2O part comes off. So a water is removed is what happens. And now a positive charge up here. I'm writing it with all the CH3s clustered together so I don't have to draw it all out. Yeah. Okay. What's next? What's the next thing that happens? Let's watch the video. Watch a little bit more of this sequence, okay? Again, studied this reaction to death. So we just did that, right? Next part? Yeah, the chloride attaches to the carbon. Now, we'll go like this. We'll say C, again, writing this part over. Again, the chlorine, and when it does it with a pair of electrons. I'm not going to draw all the electrons in there, but it has a lone pair. It actually has 4 lone pairs. But. And then what I end up with is this. And those are the 3 steps of this reaction. Now, I don't necessarily expect you watch a video and be able to do this on your own yet. Like when you take OChem, that's when you learn how to do it. You take organic. Go ahead.
Was Cl present in step 1 and step 2?
Yeah, it was just sitting there in the earlier steps. But we only used it, like if you go back up to here, it was on the slide, but it wasn't doing anything till the 3rd step, so we just don't include it till the 3rd step. Now, if you have H and you have Cl, what do you have? HCl. So when this reaction is done, it's actually you take that OH, that's called T-butyl alcohol, the one on the left, and you mix it with hydrochloric acid, and you shake it in a test tube, and the reaction's done in like a half a second. It's very fast. Okay. But the Cl isn't participating in all steps of the reactions. It's only participating in the last step of the reaction. Okay. And if you take and you add this all up together, now you guys remember Hess's law? You guys remember that? If I have, just for example, A goes to B and B goes to C, and I add these 2 reactions together, right? This is Hess's law. If I add those 2 together, what do I get to do before I add them? Well, yeah, these are delta H's. You have delta, but if I'm going to add these and get the overall reaction, right? What am I going to do with these letters before I do that? Can't remember. Well, let me write it without doing it. If I wrote A plus B goes to B plus C, what do I get to get rid of? The B doesn't really matter, right? It goes away. So before you even add them, if you see that they're there, you can cancel them out, and you can see that this A goes to C. Well, this you learned this skill in chapter 5, I think, or 6. It's called Hess's law, and you can add reactions together, and when you add the reactions together, you end up with a new overall reaction, like a net reaction. Now, if you had a delta H for this one and a delta H for this one, you could just add the delta H's and see delta H for this reaction. That was Hess's law. We're going to apply the same principle to this reaction. Yes, that doesn't want to go any higher. It's kind of that's better. Get a little more light on it. If I were to add these things up, and I'm actually not going to cross them out. I'm going to put circles and squares around them. So you see what gets canceled out, right? Oh, by the way, how many steps in this mechanism again? 3, right? And for each step, I have a reaction. These are actually known as elementary reactions. Can't see it, can you?
Why are they called elementary?
Oh, because they make up there's an overall reaction. That's the chemical reaction, and the elementary reaction makes up the overall process. Just like elementary school makes, have grades, right? Elementary levels, it's just the idea, basic part of it. Yeah. So that's terminology. That's what they call them. So I have 3 elementary reactions. they're going to add together, and they'll give me an overall reaction. That's what's going to be down here. And it's just like Hess's law. I could add it all up and then cancel stuff out, but usually people cancel stuff out and then add it together. What can I cancel? Wait. Start from the top. What can I cancel? This one? Yeah, this can go away. And the reason it can go away is because it's here. What else can go away?
CH3.
This one? Yeah. So, normally I'd cross them off, but I just want it to be real clear, like what I'm getting rid of. Can anything else be gotten rid of? Okay, so then I can add it up and I'll have my overall reaction. And my overall reaction is this. And this comes from, like I said, actually the way you do this reaction, you just mix hydrochloric acid with this and you shake it up. So some people will write this as HCl, but you can leave it as H plus and Cl minus in this matter. And then we're going to end up with this. And so that's my overall process. Okay, overall reaction. So elementary steps add together to give you your overall reaction. One of the first things you usually do when you check a mechanism is you look at what the reactants and the products of a reaction actually are, and you see if the reaction mechanism adds to give the overall reaction. What you see in the solution, right? Yeah, it's kind of this reaction is kind of interesting because T-butyl alcohol is a little bit soluble in water, but this isn't. All right, and you're making water with it. So actually, when you do this reaction and you put the hydrochloric acid into it, it's all one mixture, all homogeneous, and then you shake it for about 3 or 4 seconds just to make sure the reaction is complete. And when you're done, there's 2 layers. And this layer is less dense than this layer, so there's a thin layer of water floating on the top when you're done with this reaction. Okay. Anyways. You notice how this species here, we'll call it A. I'll call this one B. You see how they get made during the reaction and then get used up during the reaction? These are known as intermediates. They're not stable. In the reaction, they're not stable. They only exist during the reaction, while the reaction is taking place. And then it gets consumed in the reaction to produce the products. So these A and Bs, these are known as intermediates. Okay. Questions about what I wrote? A lot of terms. Mostly it's terms in this part.
Called one species. I heard you say.
Yeah, A and B are species, just like we're species. It's just a member of the chemical reaction. Right? Like we're species. It's just a term. Language stuff. Now, the first reaction that I showed you was much easier, right? I wrote it up there. And then I'm going to show you how to write the mechanism for the one on the left, and then we'll talk about how you write the mechanism for the one on the right. And then we'll do it. So, for the one on the left, it was CH, I already wrote it on the other slide, but I'm going to write it again. CH3Cl plus F minus makes CH3F plus Cl minus. So how many elementary steps? Just the one, right? So we say it's a single elementary step or a one-step reaction. Both patent legs on at the same time. Which is the slow step? Right? Well, there's only one step. So this has to be the slow step. If this mechanism is correct, and it turns out this mechanism is correct, you can write the reaction rate law from the mechanism like this. Reaction rate equals K1 is usually what they say for the first step. That would be K1. It's K1 times the concentration of the first reactant times the concentration of the second reactant. Now, if there had been a coefficient of 2 here, okay, or sorry, here, this would have been squared. So the coefficients give us, in the elementary steps, the coefficients give us the orders. So they're the same as, right, same as the stoichiometric coefficient. The other interpretation of the elementary step, okay, was part of the interpretation, is that in order for this reaction to proceed, the slowest step requires a CH3Cl and an F minus to run into each other. They have to collide for the reaction to take place. All right? Now, how do you verify this experimentally? Right, you do a rate law study. So all that stuff we talked about in the very beginning, you change the concentration of this, and you see what happens to the reaction rate. Right? If you double this and this doubles, then it's first order. If you double this and this doubles, then that's first order. In fact, they've done this experiment, it's been done thousands, maybe even more times, to verify that that's the correct mechanism for that reaction. It's been studied for all kinds of different chemical species, like different reactants for different products. So that's well established.
So it'll never be zero order.
Yeah, it could be. So how could you have a zero order, right? And I'll talk about that. It just means like the reactant that's zero order either comes after the rate determining step. Remember, this is the slow step, right? So the reaction rate, if something happens after this, and by definition it's faster because that's the slow step, it won't show up in the rate law. So you can have a zero order if it's not part of the rate determining step. That's what happens in this one. So this is a good transition. Okay, so if this was the rate determining step, okay, I could do exactly the same thing that I did for that one. I would say reaction rate equals this, a T-butyl alcohol, times H+. And I could test it by changing the H+ concentration, right, and seeing if it affects the overall rate of the reaction. If this is the rate determining step, right, where's the chlorine? It's way down here, right? It's after the rate determining step, so it doesn't show up in the rate laws, so it's zero order. You guys ever, I should have done this again. I had people filling, I made an assembly line last semester and had people making stuff. And I made somebody the rate determining step, right? So think of like, you ever worked on a school project and you're doing something and somebody else has to take it after you. They have to do something and then there's a third person and they have to do something. And this is like what you do in elementary school, right? You're all making like little squares and you pass it on, somebody glues all the squares on, and then somebody puts glitter, which is horrible, by the way. If you're before the rate determining step, you're handing stuff to somebody, but they're really slow. So then you cannot get lazy, and you just kind of like just start handing them stuff slowly so that they can keep up. What about the person after the rate determining step? They get the object that they're supposed to handle, and they're just done with it, and then they sit there and they wait for the guy at the rate determining step to hand them all the glued squares or something, right? So that's the idea. In this reaction, I have one of these is going to be slow. And it turns out it's this one. And the reason this reaction is slow is because you have to break this bond in order to make that. And when you break a bond, right, it always takes energy to break a bond. And so it turns out bond breaking is usually the rate determining step in a reaction. So the two reactants collide. They produce an intermediate species. The intermediate species then has to break a bond. That's usually the slowest step. So we're going to call this the slow step. Experimentally, it's been determined that that's the slow step for this reaction. Okay? Okay, so I'm going to write the rate law. What am I going to write? Okay, so to make life easy, right? I call this A. So reaction rate. Let me write that neater. RR, right? Equals what?
K1.
K. I'll tell you which K it is in a second. Okay. Times concentration of A. And there's one of them, right? So it's the first order. Now here's the thing. We're going to call this K1 because it's the first reaction. We're going to call this one K2. We're going to call this one K3. So we use subscripts to designate which K it is. So this is K1. Oh, sorry, K2. Didn't get enough coffee. Now here's the problem, right? In our scenario here, A is an intermediate. And you can't write rate laws that you can test for the most part by including intermediate species, because you can't control them. Like if I say double the concentration at the intermediate, how do you do that? Right? You don't actually have it. It's produced during the reaction. So there is no good way to change the concentration of A. So what we're going to have to do is we're going to have to do a substitution to replace A with reactants or products. And I'll show you how we do that. When I say substitution, I mean like mathematically, we're going to make an equation and substitute. Same substitution, okay? So I have my first reaction up here. That's where it's going to come from. That's where the substitution is going to come from. And I can rewrite my first reaction. I'm going to write it up here. I can write it as CH3 plus H plus makes A. Because it's a lot easier to write A. And this is K1. These reactions are reversible. So if the concentration of A gets high enough, A starts to decompose, starts to lose the hydrogen ion it picked up, and starts to produce the reactants again. So there's a K1 in the forward direction, and then there's a K minus 1 in the reverse. So we write it like that. So I have a forward reaction and a reverse reaction. And we write it as an equilibrium. Now I still have to get rid of A, right? But I'm going to use this to get rid of this. I'm going to do a substitution. So let me show you mathematically how we do the substitution. But I'm going to write that the forward rate is going to be this. So it'd be K1 times C CH3 times H plus. Oh, sorry, OH. It's OH, huh? Yeah, first step's OH, my bad. Let me fix that. Oops, sorry. That's the OH. I was writing the product. And this up here is also the OH. So that's what this rate is. It's the rate constant times the concentration of that OH, alcohol, times the hydrogen ion concentration. What's this rate going to be? Well, this rate is K minus 1 times A. This is the reverse rate. And this is the forward rate.
So it's not K minus 1?
What's that?
It's not K minus 1?
Oh yeah, K minus 1, thank you. If I can write that in this space. And when the system reaches equilibrium, that means the forward and reverse rates are the same, so I can just put an equal sign in here. And what does this end up being, right? So you notice in this expression, this becomes a mathematical expression. I can solve it for A. And then I can substitute into the first equation. So if I solve that for A, just divide through by K minus 1. So I'm going to put A on the left because I'm solving for A. It's going to be K1 over K minus 1 times the concentration of I should have called that something too, huh? CH3 OH times H plus, like that. That guy goes right there. And now we're going to plug it in. Okay. So I'm going to have reaction rate equals K2, that's from the top equation, from up here, okay, times what I have for A now, which is K1 over K minus 1 times the concentration of CH3OH times the concentration of H plus, like that. Now, just to finish this up so it looks more like a rate law you've seen before, they usually rewrite this as reaction rate equals K. Notice no subscript. That's the combination of K2 times K1 divided by K minus 1. Okay, so let's say K times the concentration of the first reactant times the second, like that. Now, how do you know if this is right? Well, if they tell you the second step is rate determining, then you know it's right. But to know it's right, you actually have to do the experiment where you change concentrations and see what the rates do. All right. Questions?
Can you explain the last part? We said that K2.
Yeah, so we took all the little k's, the K2, the K1, and the K minus 1, and just shoved them all together. So in this case, K is equal to K2 times K1 divided by K minus 1.
Okay, so it's not zero order, right?
It's not zero order because this is 1 and this is 1, right? What's the order for Cl though? 0. It's not there, right? Because it's after the rate determining step. So it doesn't matter.
So you wouldn't put K3?
No, there's no K3 unless it turns out this was the rate determining step. Then you'd have to put a K3 in there. And then you'd have to work all these, I'm not going to make you do that, but you'd have to work all these equations back as equilibrium, and you'd have to do a bunch of substitutions until you got rid of everything, right? So let's look at another one. Okay. I keep forgetting to remove these animations. Oops, and I go right past it. There you go. Overall reaction is this, right? 2 NOs plus H2 makes N2O plus H2 gas. And the mechanisms, there's actually the mechanism that was proposed for this reaction is that 2 NOs have to get together, okay? And they produce this intermediate, this N2O4. And then the N2O2. And the N2O2 reacts with H2 to produce N2O and H2O. So that's a proposed mechanism. First thing that you want to check when you have a proposed mechanism is, does the proposed mechanism add up to be the overall reaction? Okay. Does it? Well, we have to check, right? So if I add these two reactions together, I should be able to make it look like that. So I'm not going to actually add them. We'll cross the stuff out just to verify that it does that. What can I cross out? N2O2. Anything else? No, that's it. And if you add it together, I'll get two NOs plus H2 makes N2O and H2O. Okay. Okay. I don't expect you to be able to propose mechanisms, but I will give you mechanisms. I expect you to be able to figure out what the rate law would look like. Okay. So let's say the first step was rate determining, right? What would the rate law be? RR equals K1, yeah, times. If just the first step is rate determining, that's the slow step, and everything else after it's fast. A times, this would be NO times NO. Right? So you write it directly from, like I did for here, if this is the only step in the reaction, and it's the rate determining one, it's going to be K1 times the concentrations of the reactants, right, raised to whatever their coefficients are. So in this case, it would be NO times NO or NO squared. Like that. And this is how you get something that has to be second order. What this says is that two molecules of NO, before this reaction can proceed to the next step, two molecules of NO have to collide together. And when they collide together, right, they form this intermediate, which then quickly reacts with H2 to produce the products.
So this is second order?
Yeah, so if that's, see, this is how you test it. That the proposal now is it's second order in NO, and so you go and you change the concentration of NO. Let's say you double it. What would happen to the reaction rate? It's second order. 4 times faster. All right. We'll go 4 times faster. Okay. So it turns out in this reaction, the second step is the rate determining step. Okay. And it determines the rate of the reaction, how fast the reaction will go. So if you were to write the rate law for the second step, we'll do it on the board. If you're writing the rate law for the second step, you're going to get this. You get rate, reaction rate equals, and then it's the concentration of, or K2, because that's the second step in the reaction, right? Mechanism, times N2O2 times H2. Is everybody with me on that? What's the problem with it?
It's not canceled. Those two are canceled.
N2O2 is an intermediate, and we have to get rid of it. All right, because you can't control that concentration. So what you're going to have to do is, again, this is an intermediate. Replace, substitute. with, I'll just say reaction 1. It's not exactly that, but the equation, send it the equation from reaction 1. So again, we're going to go through and we're going to write an equilibrium expression. So I'm going to say K1 times NO squared is equal to K minus 1 times N2O4, or N2O2, sorry. And I'll do a substitution for that. So go ahead and see if you can get ahead of me here. I'm going to write it out. And this gets written as K, the overall rate constant for the reaction. Okay? Yeah, bless you. You see what I did? You with me? There's all kinds of like other questions, like why did you do that? But I'll get to it.
So you transition from the, you replace the reaction, you transition from K2 to K.
Yeah. I get rid of any intermediates. And if I'm looking at the second step being rate determining, I have to look at the reaction that's above it. So I'm going to take equation 1 and make an equation out of it so I can replace it in equation 2.
You show us how to find for reaction coefficients with like data and tables and experiments. Is there a similar way to do that with the reverse coefficients?
Oh. Yeah. Complicated. So TS, can you figure out, how do you know what this, I think the basic question is, how do you know N2O2? And how do you know that's there? Is that kind of what you're asking? And how do you know what the coefficients are? Like, what's that product?
How do you find like the K -1?
Yeah, more complicated. So N2O2 probably has, and I don't know for sure for N2O2, but it's an intermediate, right? So it gets made and then it gets used up during the reaction. So you can't really like ever measure its true concentration because it's transient. So what you do is you have to find some marker for N2O2 to measure its concentration. And usually, you know how you use the spectrovises and you measure the spectrum? Well, it's probably got a unique spectral signal, and you just measure that over time. But a lot of times the reactions go so fast, you have to cool them down. So imagine, like, because we talk about reaction rate changes with temperature, right? And if you cool something down, the reaction runs slower. If you can get it to run slow enough, then you can actually measure it by looking at its spectra. Okay, so that's about the best answer I can give you. They'll drop it into like liquid nitrogen or liquid helium, and essentially slows the reaction so far down you can measure it.
It wouldn't work the same if we knew, like, say you do the experiment, you found the Ford reaction. Couldn't you just take the concentration? I mean, you would have values for the concentrations, right?
Yeah, but because this one is, we're assuming that this first reaction at the top is fast. The presumption is it hits equilibrium very quickly. So you have to be able to measure like the transition from NO to N2O2 without any of step 2 going on.
Oh, because it just goes.
Yeah.
Oh.
So yeah, it's not easy to just measure like the one independently. Okay, so let me go back to this, right? If the first step was rate determining, right, and you change the concentration to H2, so if that was the first step, rate determining, and you change the concentration to H2, you wouldn't expect the rate to be affected because it's not part of the rate law. It's after. You said it's the first step, rate determining after the first step. So in fact, when you do this reaction, the concentration of H2 is important, so it indicates that this is a better mechanism. Having said that, and I'll talk a little bit more about like why this mechanism was written the way it was. Having said that, you can't ever prove a mechanism. You can only say it's consistent with the second step being slow, but to prove it, you have to show all possible variations of the mechanism, and you could imagine there's all kinds of things you could put up there. You could have 5 steps before, or you could have 3 steps before, or you could have 1 step like we do here, but it could be a different step. When you look at the literature and you look at burning, you like take a piece of wood or just pure carbon and you light it on fire with pure oxygen, you get pure carbon dioxide out, right? That sounds so simple, right? There's like 27 different mechanisms or something like that for the combustion of carbon with oxygen. And guys spend their lives trying to figure out what's the best way to make that happen. Not me, that's my job, but just saying. All right, a little bit more about reaction mechanisms, and then we're done, almost. I already did the deriving of the rate laws, so I'm actually skipping a whole bunch of slides because the next few dozen slides maybe are what I did on the board just now. Trying to find a good slide, but I don't see it. I don't see the one I want. Maybe it's beyond. Oh yeah. Well, let me go ahead and just write stuff on the board, and then we'll start the catalyst. Because there's a few other things I need to say about reaction mechanisms. There's 3 terms that come along with reaction mechanisms. The first term is unimolecular. Unimolecular sounds like what? One molecule, right? Unimolecular steps have one reactant. And then there's bimolecular. So what we've looked at so far, right, we've looked at a bunch of bimolecular mechanisms. Bimolecular would be like the one that's here. Figure out how to do this without being pop the back door open and that one will stay shut. Okay, so there's unimolecular, bimolecular. Bimolecular means, right, steps means 2 reactants come together. So in a unimolecular reaction, in order for the reaction to take place, you just need the 1 molecule. In a bimolecular reaction, you need 2 molecules to collide at the same time. That's not so bad. Those are the most common. Unimolecular, bimolecular mechanisms are the most common. Term molecular defines all the rest. More than 2. More than two reactants have to come together at the same time in order for reaction to take place. So this is like scheduling a meeting, okay? You have to schedule a meeting, and it's a unimolecular meeting. How hard is that? You're meeting with yourself, right? You just decide when you want to meet. You meet with yourself, whatever that means. Now you got a bimolecular reaction, right? You got to get two people together at the same time with the correct orientation, right? Thinking about the same thing, and that's a little bit harder. And then there's term molecular, and the reason there's only, because you can imagine you could have 3 molecules get together, 4 molecules get together, 5 molecules. You can see all the possibility. It's so hard for molecules to get together, more than 2 molecules to get together at the same time with the correct orientation and sufficient energy, that they just lumped them all together. And there are literally only about a handful, like 5 to 7 reactions that, of all the millions that we've observed, that are term molecular in nature. So they just lumped them all together. But it means 3 things have to come together with the correct orientation at the same time, right, with enough energy for that reaction to take place. So you notice in the last reaction, and let me go back to that last one because I just want to pop it up real quick. You could have written that as a one-step mechanism. You could have said 2 NOs get together with an H2, but that would have been term molecular. It would have said that 2 NO molecules have to get together with an H2 molecule for those products to form, and they have to get together at the same time with the right orientation and the correct energy. Anytime a kineticist, like that's what you call these people who study kineticists, see something like that, they say, well, that's probably not it. And then they try to break it up into unimolecular, bimolecular reactions. So that's what happened in this second one, right? The 2 steps proposed, bimolecular, bimolecular. Now, I don't have any slides. I just realized I don't have any slides. I don't know why I just realized. I must have deleted it. On energy diagrams for multi-step reactions, when I say slow reaction, what does that mean about the activation energy? What does it mean about the activation energy when I say the reaction's slow? It's high, yeah. Remember me going over the hurdles? I could barely walk around the class. Activation energy is high. So how does that look when you have a multi-stepped reaction? Right? So let's say I have A goes to B, and then B goes to C, and then, I don't know, C goes to D. Those are my steps, right? Each one of these has an activation energy. Because each one has a rate. What if, right, what does the energy diagram look like for multi-step? You're going to have one peak for every reaction. So let's say it's exothermic, goes like this. That's one people like to think about the most. And let's say the first step is the rate determining step. Which peak has to be the biggest? First, if the first step, if the second one is the second step will be. So if it's a first step rate determining, RDS is rate determining step, slow step. Then the first one's got to be big, and then the rest of them just have to be smaller We don't know the size unless we do other studies to figure out what the sizes are. And those aren't straight kinetic. Those aren't straight kinetic studies. But this is the first activation energy. This is this little bump here and this little bump here. Those are the second and third activation energies. They're a little tiny thing, and so the rates are really fast. So let's do one that's endothermic, okay? And we're going to do second step RDS. What is that going to look like? Big bump in the middle? Couldn't quite hear what you said. Yeah, but which one increases? Second one, yeah. So if it's endothermic, so it's going to go like this, it's going to increase. Oh, I see what you're saying. And then first step might be like this. Second step would be like this. Or the third step. And all that matters is this step is huge. Like when you draw it, it's probably not that much bigger in reality. But when you draw it to make it really clear, that would be the second step rate determining. The first activation energy would be this one. Second activation energy. Third activation energy is that one. And if the last step's rate determining, right, the third hump is the biggest hump and the other twos are smaller. And we do studies. There's studies that you can do to figure out how big that activation energy is. By changing temperature and measuring how much faster the reaction rate changes, how much the reaction rate changes by. Okay, last bit on this chapter is catalysts. Let me get to the catalyst slide, and we'll start the presentation back up here. So a catalyst makes reactions faster. It's a substance that increases the rate of reaction, but is not part of the overall reaction. So that sounds weird. Okay. So it's like this. Well, let me show you. I have an equation for the next one. This is what it kind of looks like. Okay. Oh, sorry. There's two kinds of catalysts. There's homogeneous catalysts and heterogeneous catalysts. A homogeneous catalyst, right? The catalyst is usually written on the reaction arrow. So there's my reaction arrow up here. All right. The catalyst is written on the reaction arrow. Iron chloride, ferric chloride, is the catalyst for the decomposition of H2O2. This is known as a homogeneous catalyst because it's in the same phase as the reactant. Another catalyst for this very same reaction is magnesium dioxide, manganese 4 oxide. It's heterogeneous because it's a solid where H2O is a liquid, right? And so it's in aqueous phase. So this would be heterogeneous. Now, we put them on top of the reaction arrow because they don't actually show up in the overall reaction, but they do actually participate in the reaction. They help facilitate the reaction. All right, so what's going to happen? I'm going to do it with an energy diagram. Let's assume it's a single-step mechanism, although I'm pretty sure it's not. It's actually a two-step. Let's say your reaction looks like this. And this is H2O2, and this is H2O plus O2. Like that. Exothermic reaction, okay? This is my reactants, this is my products. Now, when you go to the store, right, and you buy hydrogen peroxide, H2O2, it's pretty stable, right? You can buy it off the shelf. It lasts for, a few months. What does that tell you about the activation energy? The fact that it's stable. It's got to be pretty high. Things that are stable tend to have very high activation energy. So, like, when you buy something, like a Twinkie, and it has a shelf life of like 100 years or something, right? Its decomposition has a very high activation energy. How do you make this faster? Increase temperature, right? So you can heat it up and it'll decompose quickly. Or you can add a catalyst. And a catalyst at the same temperature makes the reaction faster. So what does it actually do? Lowers the activation energy. And it can do it a couple of different ways. Most of the time, books will draw it either like this, or they'll draw it like this. Either way is okay. When you draw it like this just stabilizes the intermediate. I don't know how. What is it telling you when you do this? Actually make a divot in between, in the middle of that. All right? You have two activation energies. Now, it's adding a step that you don't see to the reaction. And it has with low activation energy. So you haven't changed the energy of the molecules at all, but you've just created a step that's a halfway step that's easier than the overall step. I guess I try to explain it like this, but for people that are in shape, it doesn't really matter. But if you're running upstairs, right, it's easier if you take a step at a time. Then if you try to do 2 steps at a time, you go slower. I go slower anyways, going to the top. Because usually I crash and burn before I get halfway up. All right. Okay. That's kind of it. We got like 5 minutes left. We can just answer questions if you guys have any questions. I do have the notes for the next chapter, but I'll hold on to them till then. I do have also the study guide, and you're going to have to do a little graphing, so I made graph paper out of it in Excel, so you'll be able to do that. And I'll take a roll over there. So if you guys have any questions, go ahead and ask. Next week, exam on Monday and lecture. Okay? So we almost always lecture, and there's no lab except for on Wednesday we'll do a new experiment. Okay? That's been posted as well.
So we'll take the test from here and then go to the lab.
Well, okay, so what I like to do if I can, I like to lecture first, and I'll do exactly the hour, and then if I can find a room, because I have this room for only an hour and 15 minutes. If I can get another room for like 2 hours, then I can give you 2 hours to do the exam.
So what's the lecture going to be on Monday?
Equilibrium.
So it's the next?
Yeah, it's the next material, yeah.
So you're going to...
That's the only way to stay on pace, otherwise you fall behind all the time.